we have this application prompt. We have 1200 feet of fencing, and we will create a rectangular playground. So pretty much what we have is we have x. Let's label that x, and there will be 4 of them, and there will be the other side will be y. So all of these sides require a fence. So pretty much we will have 4x plus 3y equal to 1200. So that is the total fencing that we have. We try to maximize the area that is enclosed. So the area is this rectangle. One side is 2x, the other side is y. So the area is equal to the length times width, the length times width. And this is to be maximized. We need to maximize. We need to maximize area. So to be maximized. Right. Slightly prompt. There's small prompt. It need to be in only one variable. So we either have to solve for y in terms of x or solve for x in terms of y. So from this equation, I will solve for y in terms of x. So minus 4x on both sides, 3y equal to 1200 minus 4x, and then divided by 3 on both sides, y equal to 400 minus 4 over 3x. 1200 divided by 3 is 400, and so that's what we have. Y is equal to 400 minus 4 over 3x. Substitute that into this y. So the function that we're trying to maximize is 2x times 400 minus 4 over 3x. Right. We can multiply it out. That gives us 800x minus 8 over 3 x squared. So that is the function that we're trying to maximize. All right. Next, we need to have the boundary, the condition for x. X and y are the measurement, so it cannot be negative. So we have x is greater than or equal to 0, and y is greater than or equal to 0. Right. Since everything in terms of x, first we're going to have x greater than or equal to 0. Now y is equal to 400 minus 4 over 3x, and that is y has to be greater than or equal to 0 as well. So now we're just going to solve for x. Subtract 400 on both sides. We have negative 4 over 3x greater than or equal to negative 400. Right. Next, I will multiply by negative 3 on both sides just to get rid of the negatives. So we'll have x. Notice since we multiply both sides by the negative number, the inequality have to be reversed. And again, we multiply by negative 3. So negative 3 cancel. We have 4x less than or equal to negative 3 times negative 400 is 1200. Divide by 4 on both sides. We have x less than or equal to 300. So 1200 divided by 4 is 300. So combine this one and this one in our problem is this. find absolute max of the function 800x minus a over 3x squared, and have to be on the interval. The interval is x greater than or equal to 0, less than or equal to 300. Right. So that is our problem. Right. And this is the standard optimization problem. So we will find the critical numbers in the boundary of 0 to 300. So first, find the critical number. On the interval of 0 to 300. It is a closed interval. Right. I will take the derivative and make it equal to 0 or does not exist. Derivative of a, this is the function a. So we take the derivative, we have 800 minus 16 I should say 8 over 3 times 2x. Derivative of xy is 2x. Or we just have 800 minus 16x over 3. Right. So that is the derivative. We just need to make this equal to 0 or does not exist. So derivative equal to 0. So this equal to 0. Subtract 800 on both sides. And then multiply by 3 over 16. We have negative 16x. If we multiply by 3 on both sides, let's just multiply by negative 3. Multiply by negative 3 on both sides, we have 16x equal to 2400. And divide by 16 on both sides, we have x equal to 24 over 16. That is 150. Right. So x equal to 150. Right. And that's all we have. And certainly the point 150 here is between 0 and 300. So we have only one critical number in the boundary. So since there is only one critical number in the domain, we can use the second derivative test. Right. So the point here is we find one critical numbers, and of course that should be our answer. However, in this problem we need to find the absolute maximum. So whatever the point we find, we need to confirm that it actually gives us the maximum. And since this is only one there is exactly one critical number in the domain, we'll use the second derivative test. Because the derivative will be very easy to calculate. We only have the first derivative, so we will find the second derivative. The first derivative is this. That is the first derivative. So we take derivative of that, give us negative 16 over 3. And we have the point x equal to 150. So at x equal to 150, actually it doesn't matter. The second derivative is always negative now. Negative 16 over 3. And if it's negative, the graph concave down, and therefore we have the maximum. So in this, we confirm that it is going to be a maximum at x equal to 150. So this will guarantee to have the local maximum and therefore also absolute maximum. So we just say maximum here. Maximum at x equal to 150. Right. So now we just go back to our problem and we have x is 150. So y must be 400 minus 4 over 3 times x. So there's two ways to find the area. One way is we just substitute into the area function. This is the area function. We just substitute x into it, and we have the absolute maximum area. Or we're just going to find y is equal to 400 minus 4 over 3x, and we substitute 150 into it. 400 minus 4 over 3, x is 150. So that will be 400 minus 4 over 3 times 150. 3 and 150 cancel out, that's 50, so that should be 200. So we have x is 150 and y is 200, and the area is equal to, since we're going to use x and y, we can say the area is 2x times y. So now problem we have is absolute maximum area equal to 1, just forgot, right, 2x times y. Equal to 2x times y, and that gives us pretty much 300 times 200 is 60,000. Originally feet of fencing, so we should have 60,000 square feet, and that's what we have.